Hello, in this video we introduce a new type of function. It's not a polynomial, it has a lot of holes and gaps in it. In other words, it's a fancy fraction called a rational function. Let's get started. So if you remember from our previous video series when we introduced functions and their graphs, one type of graph that we looked at briefly was called the reciprocal function. And you can look at your screen at the top left corner. You'll see that graph f of x equals 1 over x. And if you remember how that graph worked, it had a gap in the middle of the graph, right? At x equals 0, we had a problem. Do you remember why? That's right, because you can never divide by 0. So the one input that was problematic, if you will, was when x equaled 0. Thus, you see that the graph broke apart at x equals 0 at what we lovingly refer to in math as a vertical asymptote, or VA for short. So the vertical asymptote is where that graph breaks apart and does not exist at that input. There are certain inputs which are not allowed or not defined for the function. So we notice here that the graph breaks apart for that reason. But notice we also might see another pattern in that graph that's going to be helpful to us as we proceed today. Notice that as our x values, I'm going to use some limit notation for you. Ready for this? As our x values, and this arrow pointing to the right means approaches, as they get closer and closer to the right, further and further to the right, that means approaching infinity, going toward the right forever. What's happening to our graph? Take a look at the piece of the graph on the top quadrant 1 portion. Notice as our x values go from 1 to 2 to 3 to 4 to 5 to 6, what happens to the actual outputs? They're going down, aren't they? There's like an inverse relationship here, it looks like. In other words, we would say that our y values, or our f of x, are getting closer and closer to a certain number. And if you think about what's happening, it's 1 over x each time. So 1 over 2, 1 over 3, 1 over 4, 1 over 5. You're getting smaller and smaller, but really your fractions are getting closer and closer to the number 0. And similarly, look what happens as we allow our x values to go to the left forever, as they approach negative infinity, in other words. This is called limit notation. You'll get used to this if you continue in math. As your x values get further and further negative, after 0, of course, at 0 the graph breaks apart, but after that vertical asymptote, as we go to the left forever, what's happening to our outputs, our y values? For example, you go from -1 to -2 to -3 to -4, etc. What's happening? 1 over -1, 1 over -2, 1 over -3. You're getting more and more negative, and you're getting closer and closer to 0. So again, your outputs, your y values, get closer and closer to 0. When this relationship holds, what we mean by that is when you go toward the extremes, if your outputs are approaching a number, we say that number is known as our horizontal asymptote. And in this case, it's y equals 0. Now, in a couple of slides, we're going to show you some tricks for how to know exactly if you have a horizontal asymptote and how to find it. Okay? But for now, I wanted to show you how you can look at this graph and answer some questions. There are other types of examples of rational functions. You see 3 of them in the box on the right side of the screen. We have 1 over x minus 4, 2 over x squared minus 3x plus 2, all over x plus 2. Each of these would be an example of a rational function. Again, why is it called rational? Because you have a ratio of 2 polynomials. So the output is no longer a polynomial, but rather a rational function. And you can see that's our definition here. When you have a polynomial over a polynomial, we have a rational function. And their graphs get pretty wonky pretty quickly. So it is important for us to pay attention to where our graph breaks apart because of zeros and denominators called vertical asymptotes, and if our graph is tending to approach any certain number or line as we go toward the extremes. So take a look at the graphs provided. Click on the Desmos link if you have the interactive notes open, and that'll be really nice for you to start to really feel your way through what rational functions are doing. Let's head over to the next slide when you're ready. In example 1 here, they've given us a picture. Now, can you tell that this picture on the right is not a polynomial, but rather a rational function? Well, let's see. The red graph here appears to have 3 pieces. It has a piece to the left of a certain number, a piece in between 2 numbers, and a piece to the right of a certain number. But there are 2 locations here which appear to be problematic for our domain inputs. Do you see what values appear to never exist? Yeah, it looks like maybe -2 and +2. At -2, the graph appears to be breaking apart, and again at +2. So notice those are actually my vertical asymptotes. at -2 and at +2. I could say x equals positive or -2. Those would both be my vertical asymptotes. Those are the lines where, the vertical lines, where the graph breaks apart. But now I can answer some questions. Let's use that limit notation once again and see how we're doing. In part A, the question says, as x approaches, and then it gives us this number here, -2, so that would be this location, I believe, -2. As x approaches -2, now one thing you might not ever have seen before is a superscript above a number. You've seen exponents of a number, but what in the world does a plus sign mean when it's up there? It really is telling you the direction that you're coming from. So if you see a plus sign up there, it means from the right. I would encourage you to pause the video and write that down, from the right. So this is really saying as x approaches -2 from the right, comma, where are your y values going? It says f of x approaches what? Well, as you're approaching -2 from the right's perspective, wouldn't that be the piece in the middle? You're approaching -2 from the right side of things. What's happening? Well, your values are getting, your outputs are getting bigger and bigger and bigger and bigger and bigger and bigger. In other words, your outputs are approaching positive infinity because you're going up forever. Positive infinity in this case, because y is approaching positive infinity means I'm going up forever. My outputs are getting larger and larger without stopping. But what about the next piece? It says as x approaches -2, and then it says negative sign up there. That means from the left. Make sure you write that in your notes. As x approaches -2 from the left, where are your outputs going? Well, -2 from the left would be this left piece, wouldn't it? -2 from the left. So again, as I get closer and closer to -2 without touching it, where are my y values tending to go? Lower and lower and lower. In other words, they're decreasing without stopping. They're approaching negative infinity. Now take a look with me at the second part of this question. It now asks us about +2. As x approaches +2 from the right, well, +2 would be this vertical asymptote over here, wouldn't it? From the right's perspective, which graph piece would I look at? The piece in the middle or the piece on the right? From the right. Well, that would be the piece on the right, wouldn't it? So from the right's perspective, as you approach 2, you're getting lower and lower and lower and lower. In other words, you're approaching negative infinity. But the second part here says, as x approaches 2 from the left, where are our outputs approaching? Where are our y values approaching? From the left would be in the middle piece. As I approach 2 from the left, my y values are getting larger and larger without stopping, so they're approaching positive infinity. Next up, we're asked to talk about extremes, aren't we? It asks us, as x approaches negative infinity, f of x approaches what? Well, negative infinity means your x values are getting more and more negative. In other words, they're getting smaller and smaller, going toward the left forever. Which piece of the graph is allowed to go toward the left forever? Well, it would be the left piece, wouldn't it? So let's take a look at what's happening as your x values get further and further negative. Where are our outputs going? Well, they're getting closer and closer to a fixed number, and that fixed number appears to be 0. I would say that y equals 0 appears to be my horizontal asymptote. We're going to define that more clearly in the next slide, but it's right now just a limit idea. Is there a limit that I'm approaching? Yeah, I'm approaching 0 as my x values get further and further negative. What about as they get further and further positive? We see that here. When our x values are allowed to continue growing forever, where are our y values approaching, if anywhere? Well, the only piece of the graph that allows x to get bigger and bigger without stopping is the piece on the right. And so I see that as I go further and further to the right, my y values are tending to get closer and closer to 0. Now, you might be a little nervous at this point. Wait a second. What if I touch 0? Is that possible? It turns out, yes, you may touch a horizontal asymptote. It's kind of like driving your car. You're in a certain lane, and you're getting closer and closer to the median. Maybe you're texting and you shouldn't be. And you're getting closer and closer to the median. You hit the median, but you get back in your lane. Same idea. You can approach something and touch it and then get back on track. And that's exactly what's happening sometimes with horizontal asymptotes. Okay, notice the difference though. A vertical asymptote is a place where nothing exists. So you'll never actually exist on that line. So how would I describe now the domain of this picture? The domain of this picture, I'm going to come on up here so I have more space. When I say the domain of this picture, I mean all of the x inputs which are allowed. Well, let's see. It looks like every x value gets reached to negative infinity and a positive infinity, but there were two parts of the graph where no inputs were allowed. Do you remember what those two pieces were? That's right, the vertical asymptotes. So we're going to need to exclude -2 and 2. In other words, if you were thinking on a number line, -2 and 2 are the problematic inputs, but technically you could be any input to the left of -2, in between -2 and +2, and then to the right of 2. But how would we use interval notation to describe this? That's right, parentheses. So I would need to say my domain includes all of the inputs to the left of -2, in other words, parenthesis -infinity, comma -2. Use the parenthesis there to indicate that you're not allowed to actually exist at -2. A bracket would indicate you are allowed to exist there. It would include it. Union symbol in set theory means or, so you can be in this interval or the next interval. The interval between -2 and +2, all of those x values are allowed, but notice I use parentheses to indicate that -2 and +2 themselves are not allowed. Union again, parentheses +2 toward infinity. So what is this describing to the reader? What is the domain here? In interval notation, it's any x value left of -2, between -2 and +2, and right of 2. Okay. So you might need to go through this one again so it makes sense before we go into the details of how to find asymptotes by hand. So on this slide, you're going to want to make sure this page of your notes is very, very clear, okay? So make note cards out of it, maybe flashcards, because this is going to be fundamental to your success with graphing rational functions. One of the first things we'll be doing in our next video when we talk about graphing rational functions in detail, we're going to look for asymptotes. And as I mentioned today, there are two main distinctions of asymptotes. There are the asymptotes that come from existence problems. For example, the vertical asymptotes, they exist when your denominator would have been 0, so we exclude them from the domain. And then there's the horizontal or slant asymptotes, which are the ideas of limits. As we go to the left and to the right forever, are we approaching a number or a line? And so we're going to put them in two broad categories. Restrictions, those are vertical asymptotes, and also holes. They also will make a restriction on your domain. But then we have the approaching asymptotes, and those are horizontal and slant. So let's take a look at our setup here. We say that a vertical asymptote is found after you first factor and cancel. So if there's any canceling to do, that is very much important that you do that first. If you do cancel any of those factors, you're going to end up with something called a removable discontinuity. It really should be called a pluggable hole because that's what it is, a fillable hole. But that removable discontinuity would be found only if you see a canceled factor. Now, if nothing cancels, that's great. That means that if your denominator is 0, it will simply produce a vertical asymptote. So what you do is you take your factors of your denominator and set them equal to 0. That will help you find any vertical asymptotes. You're going to see me do that in the next example. We already saw one earlier today, y equals 1 over x. The vertical asymptote there would just be x equals 0, right? But what if this was x minus 4 in the denominator instead? Well, it would be x minus 4 equals 0, or x equals 4 as our vertical asymptote. But if something canceled on top and bottom, that would have produced a hole instead. Okay, next up I want to look at horizontal and slant asymptotes, and this is where things are going to get really interesting. In this class, we're simply going to give you rules and ask you to memorize them. But if you go on in math, we will show you where these rules come from, and it will make so much more sense. So horizontal asymptotes, the way you're going to determine whether or not you have one is by comparing the degrees of the numerator and the denominator. So there's three possibilities. Your degree of the numerator, I'm going to call that n. You're going to see it here in my box. N is the degree of your numerator, and the degree of the denominator, I'm going to call that m. So if the degree of your numerator is smaller than the degree of your denominator, what's happening then is your denominator is growing faster, which means that your fraction is getting closer and closer to 0. So that's the case where you'll have a horizontal asymptote at y equals 0. And that's what happened with 1 over x, because the denominator had a degree of 1 and the numerator had a degree of 0. So that happened in that example. On the other hand, what if the degrees are the same? So for example, maybe you have y equals x squared plus 4 over 2x squared minus 5. Quick little example. Well, the degrees are both 2, aren't they? So if the degrees are the same, it turns out that you do have a horizontal asymptote, and you'll learn more about why that is in the next couple math classes if you continue on. But the way we're going to do it right now is we're simply going to recognize the trick that we're going to take the coefficient of the leading terms, so in this case 1 and 2, make a ratio, and that will be our horizontal asymptote. In this case, the line y equals 0.5 or 1/2 will be what we are approaching as we tend toward the extremes. So that is our example of B. And finally for C, what happens if your numerator's degree is higher than your denominator's degree? Well, it turns out you have no horizontal asymptote. So for example, y equals x squared plus 5 over x plus 2. This would be a case like C, where I have no horizontal asymptote because the degree of the numerator is higher than the degree of the denominator. The reasoning goes, since the numerator is growing faster than the denominator, there's nothing that it's approaching as far as a number is concerned at the extremes. And you'll get that proof later on in math. But there is one thing to watch out for, and that would happen in this case as well. And that one thing is right here, this last blip here, slant or oblique asymptotes. Slant asymptotes exist only if there is no horizontal asymptote. So they are mutually exclusive. You either have a horizontal or a slant. You can have neither one of them, but you cannot have both at the same time. So once you've ruled out A and B, you got to check whether or not you have C here, which is the case where, okay, I have no horizontal asymptote, but do I have a slant? The way you'll tell is if the degrees are exactly 1 apart. In this last example, notice that 2 and 1, they are exactly 1 apart, aren't they? Which means that if I were to actually divide, which is what the symbol here means, the division bar, right? If I were to really divide using my long division skills, I would end up getting a polynomial whose degree is 1 because they're 1 apart, which would mean I have a linear factor. And that linear factor would be a line, a slanted line that I'm approaching at the extremes. So you will need to use long division in order to find those slant asymptotes. And there's a little trick that we'll have to talk about when we do one of those involving the remainder and why we ignore the remainder in those cases. Okay, so at this point, please pause the video. Make sure your notes are very, very clear, that you have instructions for yourself as to when you have a horizontal asymptote and a slant asymptote, as well as the vertical asymptotes, okay? I'd really encourage you to make flashcards before you move on to attempt practicing using this information. Once you're ready, let's head over to example 2. In example 2, it says, find the vertical asymptotes, holes, and domain of the rational function f of x equals x squared minus 4 over x cubed minus 4x. Okay, so this is clearly a rational function. So what was the first recommendation anytime you're given a rational function? What should we always try to do? Factor. Good job. So go ahead and pause the video and see if you remember how to factor this one yourself. Factoring errors right here are where people most likely are going to mess up. So take your time, maybe go back and refresh your factoring abilities. If you need resources, you can always let me know. Let's see how you did. Difference of squares up top, right? So that's x plus 2 and x minus 2. Did you notice anything wonky in the denominator? What happens there? That's right, there is a greatest common factor, GCF, of x. So if you factored out the x first, you were left with x squared minus 4. And now maybe some of you did that in your head and said, wait a second, that's the same as my numerator. They're going to cancel. You're right. You could go a step further and make it very clear for the reader. You have x plus 2 times x minus 2 so far up top. And down below, we have x times x plus 2, x minus 2 again. So I wanted to be very clear for my audience what's going to happen here. Okay. So right now, before I talk about any asymptotes, let's talk domain. What are the problematic areas for the domain? What inputs are not allowed? Well, if our denominator is 0, right? So before we cancel anything, talk about the domain. This is happening before we cancel, okay? So right after we factor, let's look at the domain. Well, x equals 0 would be a problem, so we're going to say x cannot be 0, that's for sure. What else has to be excluded? That's right, x plus 2 cannot equal 0, so x cannot equal what number? -2, good job. But doesn't that also mean that x cannot equal +2 for the same reason? Good job. So there are 3 inputs which are invalid for this rational function. They would make the denominator 0 in each case. So for my domain, to show that, you could maybe use a number line to make it easier on your eyes. -2 will get excluded, 0 will get excluded, +2 will get excluded. See if you can try to write out the domain yourself now like we did in the last example. Did you get every number to the left of -2, between -2 and 0, between 0 and 2, and to the right of 2? If so, good job. Let's see what the interval notation looked like. Parenthesis, 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 parenthesis. You get the idea. So did you end up with your domain as parentheses, negative infinity to negative 2, parentheses, union, parentheses, 0, 2, parentheses, I'm going to have to slide over here, union, parentheses, so we did 0 to 2. Did I miss one? I did. You see what I did? I forgot the beginning. Let's go back and, oh, not everything. Well, since we've already talked that part through, I think we're going to be in good shape. What was the domain? It was negative infinity to negative 2. Good job. It was negative 2 to 0. Then what? It was 0 to 2. And then it was 2 to infinity, wasn't it? So there were 4 segments that were allowed when there, excuse me, when there were 3 exclusions. All right. Now, what about these holes and these vertical asymptotes? Well, we had noticed earlier that after canceling, because we had x plus 2, and we had x minus 2, and we had x, and we had x plus 2, and x minus 2, you can go back and see where that came from. We had canceled things out at this point, and we said, okay, what's going to be left? The x plus 2's cancel, and the x minus 2's cancel. Well, we would have just had 1 over x, which looks very familiar. Okay, that looks like the reciprocal function that we began this video with. And so what I notice now is that the complicated rational function is really a simple one with a couple of interesting observations. When you cancel factors, remember that canceled factors produce holes. So we are going to have 2 holes. We're going to have one hole, it's going to be a point, when x is negative 2, because that would have been the problematic region here. We're going to have another hole at the factor that was x minus 2, which would generate the hole at x equals positive 2. If you're wondering why the signs are opposite, remember what we just did with the domain? We said which of those would have been problematic, which x values? Well, when the factor equals 0. Okay, so how do you get the actual y-coordinate for the hole? Well, if the function is just the output now, it's like a little caveat because it's not exactly this function, but it has holes in it. The output is 1 over x. So if you know that those would have been the x values where we had problems, you can now input those x values into the reduced function and see what the output would have been. 1 divided by negative 2 is what? Negative half. Good job. What about 1 divided by positive 2? Just positive half. So what we're noticing right now is that if I was graphing this situation at negative 2 and at positive 2, I would have had 2 places where the graph is not existing, but it's not a break in the graph, but rather a hole. At negative 1/2, negative 0.5, and at positive 1/2, positive 0.5, I'm going to have a hole. So let me show you what that would mean. Something like this and something like this. We'd have these 2 little holes where nothing exists there, and then we continue along our merry way. What else do I know? Well, I know I still have a vertical asymptote, don't I? Yeah, it's when my denominator equals 0. So now I take my reduced version and I set my denominator equal to 0, which means x equals 0 is still my vertical asymptote. So if I was graphing this picture, that's where the graph breaks apart at that vertical line. We're also going to notice in a few moments that the horizontal asymptote will end up being 0, and that will be because the numerator's degree is smaller than the denominator's. So this graph will end up looking like this. It approaches 0 and approaches 0 at the extremes, but it also has to approach the vertical asymptote and the vertical asymptote. So our graph will tend to look something like this, and you can check yourself if you click on the Desmos link in the interactive notes. So why did the 2 holes pop up? Why are they undefined there? Because you originally had a function where in the denominator you would have had a problem if x had been negative 2 or positive 2. But after canceling, the problem went away, so we're able to continue with our graph as long as we put a pluggable hole there. All right, so let's head over to practicing horizontal asymptotes for our final example in this video. In example 3, it wants us to talk about horizontal or slant asymptotes if possible. And in part A, we have f of x equals 2x squared plus 1 over x. In B, you have h of x equals 2x minus 1 over x minus 5. Now, feel free to approach either of these problems first, whichever one you find easier. I would highly encourage you to pause the video at this point, look at your notes, and see if you can find the horizontal asymptotes yourself. Okay, so I'm going to recommend, if you haven't already done it, you can do it now. There's no problem if you want to do it now. What I would recommend you do is B first, because B is super easy once you see the pattern. In B here, do you recognize that we have the same degree? Yeah, degree is the same in both cases. This was like the second of the 3 potential outcomes here. So we have the same degree for both of them. What did that mean? Feel free to look at your notes while you're learning here. What did that mean? That meant we did have a horizontal asymptote, which means we can't have a slant asymptote. It's one or the other or neither, but not both at the same time. And it was the ratio of the leading coefficients. You can write that down again if you need to, the ratio of the leading coefficients. So what is the leading coefficient of the numerator? Isn't it 2? And what's the leading coefficient of the denominator? It's just 1. So in this case, the number that we're approaching as we go toward the extremes is just the number 2, the y value of 2. That's the output that we get closer and closer to. So if I was drawing a graph here, y equals 2, let me show you what I mean real quick. That would be this horizontal line, right? That's y equals 2. So maybe my graph's doing something like this. Maybe it's approaching like this. Maybe we have a vertical asymptote here. I'm making this part up, so don't trust the actual graph. But something like that could be happening, where at the extremes, we are approaching the number 2. That's the idea, but again, I just made up the graph, so don't trust it too much. Feel free to check out the Desmos link for the precise one. Okay, let's take a look at A now. In A, this pattern's a little more work involved, right? We noticed that, first of all, we maybe are happy that there is no horizontal asymptote. Why is that? That's right, because the degree of the numerator was larger than the degree of the denominator. Here, n was 2 and m was 1. So if the degree of the numerator was larger than the degree of the denominator, that was going to be our third option from our notes earlier. That meant there was no horizontal asymptote. What that did mean, though, is there could be a slant asymptote. It's not required. But how did we know exactly if we did have one or not? That's right. Are they exactly 1 apart? Yes, they are. So we're going to need to do some long division real quick. So to do some long division here, I'm going to actually bogart this problem here. I'm going to write x here, and I'm going to divide into 2x squared plus 1. Okay. So how do we do that long division? It might have been a while. We look at our first leading term, compare it to our inside leading term, and we ask ourselves, x times what gives me that term? It would be 2x, wouldn't it? So positive 2x. So far, we already have part of what we need. When we're trying to find a slant or an oblique asymptote, we're looking for a slanted line. The equation of a line is y equals mx plus b, right? That's the equation of a slanted line. We now have the m, don't we? We know it's going to be 2x plus something. Now, it could be 0, it could be negative 5, we don't know yet. Let's continue. You multiply 2x by what's in front, that's just 2x squared, and then you subtract, which in this case is going to cancel out that term completely. At this point, we bring down our next term. Notice 0x, so you could write 0x if you want. That was 0x technically. And then the plus 1. Okay, so you ask yourself, x times what gives me 0x? Well, that's just 0. Kind of boring, isn't it? And now we have our y-intercept. Because if you multiply 0, you'll get 0x plus 0. Nothing there. When you subtract there, notice what happens? The 0x's are gone. That's 0 minus nothing is still nothing. But 1 minus 0 is 1. Now, this is the problem some students struggle with. What do I do with that remainder? Normally, you have to talk about a remainder, right? But if the whole point of this is to say what is happening at the extremes, that's what we're talking about. As x approaches infinity, what's happening? Normally, you would have said, take my remainder and put it over whatever's in front, right? But what would happen as you allowed x to get bigger and bigger? 1 divided by 100, 1 divided by a million, a billion, a trillion. Aren't you getting closer and closer to 0? So it turns out you get to ignore remainders when you're using long division to find slant asymptotes. This is the only time where you can just throw out a remainder, say I don't need it, because we're talking about a limit idea. As your denominator gets bigger and bigger, that whole fraction will get closer to 0, so we don't need to discuss it if we're just looking for the limit. So in this case, we would say y equals 2x is the equation of my slant asymptote, meaning if I was interested in this picture, remember how to graph a line, you would have a y-intercept of 0, you'd go up 2 and right 1. You could also go down 2 and left 1, and this would be your slanted asymptote. What that could mean, for example, if you also had a vertical asymptote, which I believe this one does at 0, it could mean that your graph ends up looking something weird like this. And you're going to talk more about these graphs with me in our next video, okay? So slant asymptotes will be very helpful for drawing certain types of rational function graphs. Okay, so we've done a lot in this video. We've introduced 3 different types of horizontal or slant asymptote variations. We've also introduced holes and vertical asymptotes and limit notation. So it's up to you now to make flashcards, make sure you know which is which, and become proficient so that we can next time graph rational functions together. I'll see you then.